Hi, and welcome again to my Physics Online video lecture series. Today's video, we're going to be talking a little bit about angular momentum. This is going to be an introduction to this topic of angular momentum and a few of the basic ideas behind it. This is a continuation of our discussion of rotational dynamics in our introductory physics course. So at this point, there's quite a few things that kind of lead up to this. It's almost a bit much to say what is it that we need to recall, but let's recall a few basics. For starters, we have the linear momentum idea. So linear momentum, and linear momentum was represented by a p, and it's given by an object's mass times its velocity. Second, we have Newton's second law. So Newton's second law was originally presented to us as sum of forces is mass times acceleration, but we later realized that this actually could be recast in terms of linear momentum so that the sum of forces acting on an object was the rate change of the object's linear momentum. Next up, we have that there is rotational analogs to some things. We had energy, so kinetic energy for translation. So kinetic energy was given by K is 1/2 mv squared, and this was translation. Okay, then we have rotational analogs to various of these things. So analogs to these. Well, we have rotational kinetic energy is equal to 1/2 times I times omega squared. We had that torque is given by R cross F, and the sum of torques on a system was I times alpha, and that's where we are. So P, there's some analog for P that both could fit with this equation, and it could just fit as the analog for momentum. All right, and the answer is yes. So in rotational motion, we also have momentum. Specifically, it's called angular momentum, and angular momentum is variously represented using the letters L and J. Generally speaking, we use a capital L to represent angular momentum. Sometimes this one's just called total angular momentum. We could use a J to represent specifically orbital angular momentum, and then S in quantum mechanics represents intrinsic angular momentum or spin. But we're just simply going to use L for our purposes, and the way that it's defined is that L is defined as R cross P, so it's another cross product. So this right here gives us the definition, the diagram that goes with that definition. Let's say that this right here is my axis of rotation, and I happen to have an object which is moving off in some direction, for example like this, and I happen to have defined this as my axis of rotation. Here would be my R vector. This would be my P vector, which again is m times v. The cross product is going to be the cross product of this vector to that vector. Remember that we can use the right-handed rule, and the right-handed rule essentially means like go ahead now and move the P vector down here somewhere. So if this is R and this is P, then angle theta would be this angle right here, counterclockwise from R to P, and L would be mRV, that is mv times r, times the sine of this angle theta. So that gets you your angular momentum magnitude. Right-hand rule again applies. Basically, index finger along the first vector in the cross product, which is the r vector, middle finger along the second vector, which is the p vector, thumb points in the direction of the resultant vector. For the pair that I've drawn here, that means that the angular momentum vector is pointing up out of the screen towards you. And again, you can figure out whether it's up or down by using this sine of theta. If theta is between 0 and 180 degrees, sine of theta will be positive, and so this vector points up. If you've got a piece of paper that's lying flat on the table, it points up out of the paper. If you're looking on a screen, or if you're drawing on like a board on a wall, something like that, then sine of theta being positive means the vector points out of the wall towards you. If it is going to be negative, then this vector would point downward or into the wall or into the screen. Other point about angular momentum, so coming back to this little drawing of the axis of rotation and the object that is moving about this axis of rotation, we know that this object, if it's actually going about an axis of rotation, is going to describe an orbit more or less like this. So again, L is equal to m times r times v times sine of whatever this angle is. But if this is a solid object, so that I have some individual points that I can define for this motion, maybe one's there, maybe another one's here, going about a somewhat smaller circle. So this would be R1, this would be R2, this would have mass M2, this would have mass M1, this has some velocity V1, this has some velocity V2. This guy will now have L2 as M2, R2, V2. We can always add them together, but ultimately, if you have a solid object, for example, the grindstone wheel, that is spinning about some axis of rotation, and we want to know what is the total angular momentum, we'd have to add up all the momentum of each individual piece, but we can more simply do that by converting into the rotational system, and we get L is equal to I times omega. So the magnitude of angular momentum for a solid object which is rotating about an axis becomes I times omega. Okay, so that gives us the third sort of form of this equation. And that gives us an equation that's useful if you have an actually solid object. Before we move on to doing the examples, I should state what the unit is for angular momentum. The MKS SI unit is the joule dot second. So joules dot seconds is the units for angular momentum. For our first example, we want to know what the angular momentum is for a tether ball about its post if the ball's tangential speed is 4.4 meters per second. So this right here would be your V, this right here would be M, and then you have a tether of length 2.8 meters, tether making a 45-degree angle with the post. So in some sense, this is the theta for your sine theta, and this right here is the R for that cross product. If I was going to draw this out, by the way, you've got your post here, you've got your tether ball. This distance right here could represent like R perpendicular. and this right here would represent my speed v. But from the side, and by the way, L would be m r perpendicular v, which is by definition mrv sine theta. From the side, I have my post like this, and then I've got a tether which has a given value of r here and a tether ball. This right here would be my r perpendicular value, and this right here is my angle theta. So basically what you would do to solve this is, again, L is mrv sine theta. Using the numbers given, this is 2 kilograms, so 2.0 kilograms. R is 2.8 meters. V was 4.4 meters per second. And then sine of 45 degrees. This is root 2 over 2 is the sine of 45 degrees. You can plug it all into your calculator. What that's going to give you is about 17.6 joule seconds for this system. So yeah, 17.6 joule seconds. Let's do a second example, this one with a solid object that is moving about its axis. So if we wanted to figure out the angular momentum, L should look like I times omega. Now what we're given here is essentially like a frequency but in minutes. We're given a radius r, and we're given a mass m. So, and we're told that it's a solid disk. So solid disk basically means that you're looking at I is equal to 1/2 mr squared. And remember that frequency is given by omega via omega is 2 pi over f, but that needs to be in radians per second, and so f needs to be converted to revolutions per second rather than revolutions per minute. Whoops. So we've got 72 revolutions per minute. That means that the frequency is roughly 1.2 revolutions per second. Okay, and so that means that omega is equal to 1.2 times 2 pi. So 1.2 times 2 is 2.4 pi, and that's in radians per second. So what we end up with is 1/2 mr squared omega, which is 1/2 times mass, which was 24 kilograms, times radius, which is 0.25 meters squared, times this 2.4 pi radians per second. This one's actually calculator worthy, so let's plug it into the calculator. This gives us L is 1.8 pi joule seconds, or if you want to use the approximation of pi, then you would end up getting, rounding to 2 sig figs again, you got 5.6548, so let's call that about 5.7 joule seconds. All right, so that has been 2 examples of angular momentum to go with this introduction to angular momentum. That's all for today's video. I hope you learned something from it, and as always, thanks for watching.